All right, what does this tell us? It says, and actually it's true of functions as well as sequences, but we're interested in sequences, which is saying that the following sequences are ordered according to increasing growth rates as n goes to infinity. So, in other words, these functions, functions of this type, are significantly less than functions of these type, which would be significantly less than functions of these type, which are less than these, which are less than these, which are less than these, and so on. Okay, so a couple things. What in the world is that? So we'll make a note. That symbol is not one maybe you're familiar with, but that symbol means significantly less than. In other words, a lot less. Right? Okay, now let's look at these. We have a logarithmic function here. So we have a log function, right? That's what this is. This is a log function, right? Any log to any power. Logarithmic functions grow very slowly. So a logarithmic function is going to grow slower than a power function, which is this one. This is a power function, right? You're taking your n to a power. Remember, wherever n is, that would be like x in a regular function, right? So a logarithmic function is less than a power function. A power function is less than a power times a logarithm because they're being multiplied. Keep in mind, by the way, that we're only talking about this as n goes to infinity. So we're only talking about positive values, right? All right, so that's a power times a log, which isn't very common to find, but nevertheless, there it is. So power times log. All right, what about this one over here? Well, this is kind of an expanded power function. You're making it an even bigger power. Instead of just p, it's p plus s. So this is an expanded power function, right? So it's even larger. All right. But we learn in algebra class that no matter what power function you got, in the long run, as n goes to infinity, it will lose out every day of the week to exponential functions. Exponential functions are infinitely larger than power functions. That's what this is saying. Expanded power functions are infinitely larger than power times log. Power times log is infinitely larger than power. Power is infinitely larger than log. Again, as n goes to infinity, as we're heading out, right? Okay, so then the exponential function is infinitely less than a factorial function. A factorial function is crazy large, right? Factorials, I mean, think about infinity to the factorial power, right? So it's infinity times infinity minus 1 times infinity minus 2, et cetera, et cetera, et cetera. These are much bigger, significantly larger than an exponential function. And then the tower function, which is what this is called. So a tower function is when you take infinity to the infinity power. It sounds sort of like kids on a playground. I hate you, infinity to the infinity power, right? This is the largest. This is the most significant, right? So this is so astronomically large. It's infinitely larger than a factorial, but a factorial is infinitely larger than an exponential. Now, the real trick of these is the part that I haven't talked about yet, which is discussed right up here. If a sub n appears before b sub n in the list, then when you take the limit as n goes to infinity of a sub n divided by b sub n, in other words, you're taking a smaller function dividing it by a bigger function, then that limit as n goes to infinity will be 0, period, right? If you take a smaller function divided by a larger function, or smaller sequence divided by a larger sequence, right? That's what's happening here. Small divided by a larger one in the grand scheme of things, it will be 0 every time. A factorial will totally beat out a power function, right? It just has no chance. The power function has no chance of winning, right? And then right here, if you take the bigger function, right, something over on the right, and divide it by something on the left, even if it's the tower divided by the factorial, it doesn't matter. That tower is infinitely larger than that factorial, and it will win, right? So this is taking one of the larger ones, right here, larger divided by smaller. So the way this works is the smallest one is over here, The largest one is over here. And they're on a spectrum, if you want to see it that way. They're on a line, right? A very well-defined line. Now we can use this to find the limits of these sequences. Now keep in mind, all this is for sequences and for the fact that these are always positive and we're heading towards infinity. They also work for functions as long as you're heading towards infinity anyway, but irrelevant. Okay, so let's look at our types. If I want to call these types, so, and by the way, it said all real numbers positive, right? So this is a log divided by a power function, right? So that's a logarithm, that's a power. Power because it's n to the 1. So who's going to win? If I take a log and divide it by a power, that's smaller than that. The log is smaller than the power, right? So it's to the left, smaller, and then this is larger. What that means is that the limit as n goes to infinity of that sequence, I'm just going to call it a sub n. I should have done that in the first place. Of a sub n is 0. Period. The end. And the reason is because a power function, well, let me put it this way, a log function is significantly less than, read, a whole lot less than a power function in the long run as n goes to infinity. Okay? FCN, by the way, is a quick abbreviation for function, so we don't have to bother with it. All right, what have we got here? Well, we've got a power times a log, right? So we have up here power times log, and we're dividing it by n to the 5.003, right? Which is this one right here. So look what's happening. It's n to the p, n to the 5, times that log, but then it's n to the 5.003. So s is 0.003. It's a sneaky one. This is an expanded power, right? We're taking the same power. This was 5, and then we're making it 5.003. Sneaky. That means that this one's going to win, right? In the long run, that 5.0003, that little 0.0003, as I head towards infinity, that will end up winning out. So that means that it's smaller over larger. So that means the limit as n goes to infinity of a sub n, or this will be b sub n because this is b, so I'm going to call this b sub n, is 0. I don't have to show all the work and all that stuff. All I have to say is because a power times a log is significantly less than an expanded power. I'll just write expanded power. Now, I know what you're thinking. You're thinking, well, what if it was 4 and 5.03? Well, then it would lose even more, right? Because 4 is less than 5. What makes these two even close is the fact that it's 5 and 5.003. If this power was like 2, it wouldn't make any difference. Now, what if this power was 6? Well, then that's a larger p. And if it was 6, and then this one would be 5, and then the lower one would be losing out. So I guess I can make a little note of that. Here. If it was n to the 6th natural log of n over n to the 5.003, then would actually go to infinity. Because that's a power times a log. It's actually a expanded power times a log divided by just a regular power. That's not expanded really from this. This is not larger than that, right? So it has to be a larger power. So I guess when I say expanded, I mean a larger power than what was over here. So I guess I could put that larger right there. So larger power. So that's a smaller power. That's a larger power. The larger power will beat the smaller power, especially because it's multiplied by log, which makes it even bigger, right? So this is really going to win, right? So this one would actually go to infinity, the one that I have right here. This would be infinity. So the limit as n goes to infinity, I'm going to call it e sub n because it's just a made-up example, would be infinity for this one. All right, now let's get to the really fun ones. 4 to the n is exponential. Okay, so 4 to the n, n to the 4th. So that's an exponential divided by a power. I remember Algebra 1. Do you remember Algebra 1? Exponentials totally beat out any power, right? Completely. So the limit as n goes to infinity of c sub n, I'm going to call this cn, why not? Because it's letter c, would be infinity, right? Because exponential functions are well, I was going to put exponentials, well, I'll just do it. Exponential functions are significantly greater than any power function. Going the other way makes it significantly greater than, as opposed to significantly less than, which is up above, right? In other words, it's hella greater than power functions, right? And everybody in algebra learns that, right? Okay, then what about this one? Well, that's an exponential function, which is quite large, but it's divided by something that's even bigger, a factorial. And that factorial will totally win, right? Factorials are significantly greater than exponentials. They're to the right. So therefore, this is 0. The limit as n goes to infinity of d sub n, I'm going to call that d sub n, is 0. Because a factorial is significantly greater than an exponential. If you reversed it and took, I'm just going to make up one. So if I make a sequence that's n factorial over 4 to the n, 4 to the n, I'll call that f sub n, because I already have e sub n made up over here. That would be the limit as n goes to infinity of f sub n would be equal to infinity, because the factorial is infinitely larger than the exponential. Again, same reasoning, right? The reason works out. So if you put the bigger one on top, it'll be infinity. If you put the bigger one on bottom, it will go to 0. That's what the theorem is telling us above. And boy, do we use this. We use it a lot. Keep in mind this last one in particular, that's key right here. This one right here that we saw. That's developing this fact that we need desperately later on in this chapter, which is that if I take any constant k, any constant, and I raise it to an exponential power, but then I divide it by n factorial, that will always be 0, right? Because an exponential is, well, yeah, because k to the n, which is exponential, is significantly less than any factorial. Well, not any factorial, n factorial.